Hold up a piece of glass. Go on, imagine it. A clean, ordinary, flat piece of window glass. You can see right through it. You have done this every day of your life, and you have never once been confused by it, and that is exactly the problem. Because if you actually sit down and try to figure out what glass is doing to light, you will run straight into one of the strangest puzzles in all of physics. A puzzle so strange that Isaac Newton could not crack it. A puzzle so strange that the wave theory of light, which works beautifully for almost everything, collapses right in front of your eyes when you try to use it here. And a puzzle so strange that, even today, the only honest explanation we have requires you to accept something about nature that most people would call insane. So let me start with the simple part, the part you think you understand. You shine a beam of light at a piece of glass. Most of the light goes straight through. That is why windows work. That is why you can look outside and see the trees and the sky and the kids running around. Glass transmits light. Fine. Obvious. End of story. Except it is not the end of the story. Because here is what you might not have noticed. Some of the light does not go through, some of it bounces back. You can actually see this if you look carefully. Stand in a lit room at night, facing a dark window. You see your own reflection, not as bright as a mirror, but it is there. The glass is reflecting some of your light back at you. How much? About 4%. Out of every 100 photons you fire at the front surface of that glass, about 4 bounce back. The other 96 go in, and then when those 96 reach the back surface of the glass, another 4% of those reflect again back into the glass. So you lose a little going in and you lose a little going out. Ordinary enough, nothing shocking so far. But wait, let me ask you something that sounds like a ridiculous question. Does the amount of light reflected from the front surface depend on how thick the glass is? Think about that. A photon hits the front surface. It either bounces back or it goes through. Why would it care what is happening on the other side? The back surface could be a millimeter away or a mile away. The photon hits the front. It makes its decision right there. How could the thickness of the glass possibly matter to the front surface reflection? And yet, if you actually do the experiment carefully with light of a single color with well-polished surfaces, you find something that makes no sense at all. The total amount of light reflected from the piece of glass as a whole, the light bouncing back from both surfaces combined, does not stay at some fixed number. It changes. It depends on the thickness. For certain thicknesses, you get no reflection. 0. Not 4%. Not 8%. 0. The glass reflects nothing. All the light goes through. For other thicknesses, you get 16% reflected. 16. That is 4 times the normal single surface value. And as you slowly increase the thickness, the amount of reflection goes up and down, in a beautiful, regular repeating cycle. 0, then 16, then 0, then 16, over and over again, tied precisely to the thickness of the glass. This is not something I am making up. This is an experimental fact that has been measured with extreme precision, and it drove Newton absolutely mad. See, Newton had done the experiments himself. He pressed a curved lens down onto a flat piece of glass, creating a thin film of air between them. A film that got thicker as you moved outward from the center, and he shone light on it. What he saw were rings of color, bright rings and dark rings, alternating. At the center, where the 2 pieces of glass touched and the air gap was essentially 0, one color. A little further out, where the gap was a tiny bit wider, a different color. Then dark, then bright again, ring after ring after ring. We call these Newton's rings today, and you can still see them in any optics lab. Newton was a particle man. He believed light was made of little particles, corpuscles he called them, and corpuscles should behave like tiny bullets. A bullet hits a wall, it bounces off or punches through. It does not stop and ask how thick the wall is, but his own experiment showed him, undeniably, that the amount of light reflected depended on the thickness of the air gap, down to incredibly small distances, smaller than 1/1000th of an inch. Somehow Newton's corpuscles of light were behaving as though they knew the thickness before they decided whether to bounce back. He wrestled with this for years. In his great book, The Optics, published in 1704, he laid out a strange idea. He said the corpuscles of light must go through fits of easy reflection and fits of easy transmission. As a corpuscle travels, it oscillates between a mood of wanting to reflect and a mood of wanting to pass through. So when it arrives at a surface, whether it bounces back or goes in depends on which mood it is in at that moment. And the cycling of this mood is what produces the ring pattern. That is a beautiful guess. It captures the periodicity, the cycling, and it gives quantitative results that match what the modern wave theory predicts. Newton measured the spacings of his rings and got numbers that hold up to this day. But he could never explain what caused the fits. He invoked vibrations in some kind of ether, a subtle medium pervading all of space, and suggested these vibrations could put the corpuscles into their alternating moods. But he was honest. He wrote essentially that he did not know what the fits really were. He could describe them, he could use them to calculate, but he could not explain them. I love Newton for that. There he was, the smartest person of his age, arguably the smartest person of any age, and he looked at a piece of glass and said, in effect, "I do not understand what light is doing here." It is a sign of a great scientist that he knows what he does not know and is willing to say so plainly. And there the puzzle sat, unsolved, for more than a century. Along comes the wave theory. In the early 1800s, Thomas Young in England and Augustin Fresnel in France showed that light behaves like a wave. Light is not a particle, the wave people said. Light is a wave, like a ripple on water or a vibration of a string. And waves, it turns out, explain the reflection pattern beautifully. Let me show you why. When light waves hit the front surface of the glass, some bounce back. When the rest reach the back surface, some bounce back from there. Now you have two reflected waves, one from the front and one from the back. And here is the key. Waves can overlap. Two waves can occupy the same space at the same time. When they do, they combine. And how they combine depends on whether they are in step or out of step with each other. Imagine two people on swings, side by side. If they are swinging in perfect time, their combined motion is big and bold. That is two waves in step, what we call constructive interference. But if one person is swinging forward while the other swings backward, their combined motion is small, maybe even zero. That is destructive interference. For the light reflected from glass, the wave from the front surface and the wave from the back surface will be in step or out of step, depending on how far the second wave had to travel, which is twice the thickness of the glass, since it goes in and comes back. And in step means the crests line up. Out of step means the crest of one lines up with the trough of the other. When the thickness is such that the extra distance is a whole number of wavelengths, the waves reinforce. Maximum reflection. When the extra distance is a half wavelength off from that, they cancel. Zero reflection. As the thickness increases smoothly, the reflection cycles smoothly from maximum to zero and back. The whole pattern falls right out of the wave picture. And here's something extra that the wave theory explains. I mentioned the pattern depends on the color of the light. Red light has a longer wavelength than blue light, so the thickness that gives zero reflection for red is different from the thickness that gives zero reflection for blue. If you shine white light, which contains all colors, onto a thin piece of glass, each color has its own cycle, and different colors reflect at different thicknesses. The result is a display of colors. You see this every day, though you might not have realized what you were looking at. Soap bubbles. The shimmering colors on the surface of a soap bubble are exactly this phenomenon. The thin film of soapy water acts like a thin piece of glass, reflecting different colors from different parts of the bubble where the thickness varies. Oil on a wet road produces the same rainbow. So does a thin coating on a camera lens. All of it is the wave theory of light at work, beautifully confirmed. So the wave theory wins. Problem solved. Glass is explained. Go home. Except it is not solved. Not entirely, because somebody then went and did something the wave theory was not prepared for. They turned the light source way, way down. Dimmer and dimmer and dimmer until individual photons were arriving one at a time. You can actually detect this with a device called a photomultiplier. It is a marvelous instrument. A single photon hits a metal plate inside it and knocks loose one electron. That electron hits another plate and knocks loose several more electrons. Those hit more plates. By the end of this cascade, you have an enormous burst of electrons, enough to make a loud, clear click. One photon, one click, every time. And when the light is very dim, you hear individual clicks. Click, 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 silence, click, silence, click, click. Each click is one photon, one indivisible packet of energy. There is no half click, no quarter click, no soft, whispery little click. Every single click is exactly the same loudness. This is a disaster for the wave theory. A real disaster. Waves can be any size. You can have a tall wave or a tiny wave. Turn the volume down on a wave and it gets smaller. The energy spreads out continuously. There is no minimum chunk, but light does not behave that way. When you dim the source, the light does not get uniformly fainter. Instead, you get full-strength clicks, just fewer of them. The energy arrives in identical packages. It is as if you were listening to rain on a tin roof. You can have a heavy rain or a light drizzle, but each individual raindrop makes the same ping. The drizzle does not produce quieter pings. It produces the same pings, just fewer per second. That is exactly how light behaves. Each photon is a raindrop, and the intensity of the light is just the number of drops per second. So light is definitely arriving as particles. Individual, indivisible, identical particles. Each one either reflects or transmits. There is no splitting. There is no photon that half reflects. 100 photons go in, 4 bounce back, 96 go through. But you cannot tell in advance which 4 will bounce. It is random. Completely, stubbornly, irreducibly random. Imagine standing at the glass with your photomultiplier. A photon arrives. Click, it reflects. Another photon arrives. Same color, same direction, same everything. It goes through. No click. Why did the first one bounce and the second one pass? Nothing was different about them. Absolutely nothing. And yet they did different things. The wave theory cannot explain this randomness. A wave hits a surface, and some fraction of the wave energy reflects. Always the same fraction for the same conditions. There is no dice throwing in classical wave theory, so the wave theory gets the overall pattern right, the cycling of 0 to 16%, but it cannot explain why individual photons make individual choices. And the particle theory can explain the individual choices, the clicks, but it cannot explain why the choice depends on how thick the glass is. This is the corner nature has painted us into. Neither the pure particle picture nor the pure wave picture works by itself. What we need is something entirely new, and what we got eventually is quantum electrodynamics. QED for short. And it is, in my humble opinion, the most successful theory in the history of physics. It predicts some quantities to better than 10 decimal places. 10. That is like measuring the distance from here to the moon and getting it right to within the width of a human hair. No theory in any science ever has been more accurate than that. So let me tell you how QED handles this glass puzzle. And I have to warn you, the answer is going to sound crazy. In quantum electrodynamics, you do not ask, will this photon reflect or transmit? You cannot ask that. Nature will not answer that question. What you can ask is, what is the probability that this photon will end up at the detector behind the glass versus the detector in front of it? That is the only question nature permits, and QED gives you a method for computing the answer. The method uses what I like to call little arrows. Imagine each possible way a photon could travel from the light source to the detector. For each possible path, you draw a tiny arrow. The arrow has a length and a direction. The length is always the same for a photon in empty space, but the direction, the angle the arrow points, depends on how long that path takes. Think of it as a tiny clock hand, a stopwatch if you like. The stopwatch starts ticking the moment the photon leaves the source. The hand spins around at a rate determined by the color of the light. Red light, the hand spins slowly. Violet light, it spins fast. Blue is somewhere in between. And when the photon arrives at the detector, wherever that stopwatch hand is pointing at the moment of arrival, that is the direction of your arrow for that particular path. So each path gets an arrow, and the arrow's direction depends on how long the trip took. Short trip, the hand has not turned very much. Long trip, the hand has spun around many times. Different paths take different amounts of time, so their arrows point in different directions. To get the total probability that a photon goes from the source to some particular detector, you add up all the little arrows from all the possible paths. You line them up, nose to tail, like a chain, and you get one final arrow from the start of the first to the end of the last. The probability is the square of the length of that final arrow. Let me say that again because it is important. The probability is not the sum of the lengths, it is the length of the sum. You add the arrows as arrows, nose to tail, respecting their directions, and then you square the length of the result. This is crucial. This is the source of all the interesting behavior. If two arrows point in the same direction, the final arrow is long and the probability is high. If two arrows point in opposite directions, they cancel. The final arrow is short or zero, and the probability is small or zero. This adding with directions is what gives rise to everything people call interference. That sounds like a lot of work. Every possible path? There are infinitely many paths from the source to the detector. The photon could go in a straight line. It could zigzag. It could go to the moon and come back. You have to add arrows for all of them. But here is the miraculous thing. Most of them cancel out. The crazy paths, the ones that go to the moon and back, their arrows spin wildly and point in all different directions. When you add a bunch of arrows pointing every which way, they cancel to nearly nothing. The paths that matter, the ones that contribute to the final arrow, are the ones near the path of least time, the shortest route. The arrows for those paths all point in nearly the same direction, so they add up. This is how a photon knows to go in a straight line. It does not know, it explores every path. But the contributions from the sensible paths add up, and the contributions from the crazy paths cancel out. The net result looks exactly like a photon traveling in a straight line. And this, by the way, is how you derive all of classical optics from QED. The law that says light travels in a straight line, it is not a separate rule. It falls out of the arrows. The law that says the angle of incidence equals the angle of reflection when light bounces off a mirror also falls out of the arrows. The law of refraction, Snell's law, the one they taught you in school about sines and angles, falls out of the arrows. Every rule of classical optics is just an approximation that emerges when you add up an enormous number of arrows and the crazy ones cancel. But sometimes the crazy ones do not cancel, and that is when you get diffraction and interference and all the phenomena that seem to defy common sense. Those phenomena are not special cases. They are what happens when the geometry is set up so that the crazy paths happen to produce arrows that add up instead of canceling. Beautiful. But we are supposed to be talking about glass. So let me get back to the glass. A photon hits a piece of glass. In the QED picture, we do not say it hits the front surface and bounces or passes through. We say the photon can be scattered by any electron in the glass. Every atom in the glass has electrons, and any of them could, in principle, interact with the photon and send it back the way it came, or forward, or off at some angle. So instead of two reflections, one from the front surface and one from the back surface, we really have an enormous number of possible scattering events, one for each electron in the whole slab of glass. For each of these scattering events, there is a little arrow, and the direction of each arrow depends on when the scattering happens, which depends on how deep into the glass that particular electron sits. Now, here's the trick. You add all those arrows together for the electrons near the front surface, and they add up to one arrow. You add all the arrows for the electrons deep in the middle of the glass, and something remarkable happens. They cancel each other out. The arrows from the bulk of the glass, from the interior, all point in different directions and sum to zero. The only arrows that survive, the only ones that do not cancel, are the ones from near the front surface and from near the back surface. So even though the photon could scatter from any electron in the glass, the net effect is the same as if it only bounced off the two surfaces. The interior of the glass contributes nothing to the reflection. This is not an assumption. It is a consequence of the mathematics. QED predicts that glass behaves as if it has two reflecting surfaces and a transparent interior, which is exactly what we observe. And the thickness dependence, that falls right out of the arrows. The arrow from the front surface and the arrow from the back surface point in different directions, and the difference in their directions depends on how long the photon spent traveling through the glass, which depends